Okay, today we're going to work on Chapter 19's homework, and I want to apologize for this being late this week. My job's been sort of busy, so we're going to start, and I'll try to go through these fairly quickly, although there are a lot to do here. Number 4. Number 4 states singly charged gas ions are accelerated from rest through a voltage of 13 volts. At what temperature will the average kinetic energy of a gas molecules be the same as those given to these ions? Okay, you have to go back several chapters to find the relationship between temperature and kinetic energy. And I think it's in chapter 14, but the kinetic energy of a gas is 3/2 times a constant, which I'm going to call KB because it's called Boltzmann's constant. If you want to look it up, it's in the gas law chapter, times the temperature in Kelvin. And related to that is the electrical potential energy. And you have to think of electrical potential energy as like elastic potential energy, which is like gravitational potential energy, and the fact that it's energy that is available and can occur if the situation changes. So for example, if you have a rock on the top of a cliff, it has a certain gravitational potential energy, which if it falls off the cliff, then it achieves that energy in the form of velocity. On the other hand, the elastic potential energy, you'll remember if you pull a spring back and hold it, it has a certain energy available in that elastic spring that is only realized as if you let it go. And so the electrical potential energy is equal to the charge times the voltage. Voltage is a measure of electrical potential. And so in this case, this electrical potential energy is equal to the kinetic energy here. And so you can set these two parameters equal to each other. So 2/3 Boltzmann's constant times the temperature is equal to QV. And if you solve this for T, which is what they were asking for, that's going to be 2/3. That's moving this 3/2 over. QV divided by K Boltzmann. And then, so that's going to be 2/3 times, and the charge, it's a singly charged ion. So that's 1.6 times 10 to the minus 19 coulombs times 13, which is the voltage, divided by, and Boltzmann's constant, if you look that up, it's 1.38 times 10 to the minus 23rd. And so if you get 100,000 degrees Kelvin, 100,000 degrees Kelvin. So that is the temperature necessary to be equivalent to this charge. Number 8. Number 8 states, a 12-volt battery operates a bottle warmer and it heats 50 grams of glass, 250 grams of baby formula, and 200 grams of aluminum from 20 to 70. So how much charge has to move through the battery? Okay. So we have, and I'm going to use QH. Well, let's use big Q. That's the heat. And you'll remember from our previous situation that the heat is M, the specific heat, times the change in temperature, M being the mass. And you have three things here that you're heating up. So the QH has to equal the mass of the bottle times its specific heat, which I'll come back to in just a second. And the change in temperature is 70 degrees, plus the mass of the formula times its specific heat, which we'll come back to in a second, times the change in temperature, plus the aluminum times its specific heat times the change in temperature. Now, it gives you, in the problem, it says that you assume that the formula has the same specific heat of water, and you have to use the specific heat in terms of joules. And so for water, that's 4180 per kilo, or 4.8186 joules per gram per degree centigrade. For aluminum, it's 0.9 joules per gram per degree centigrade, and for glass, it's 0.84 joules per gram degree centigrade. And if you do all this math, you end up with the amount of heat necessary. And all of that heat has to come from the movement of charge. So all of that heat has to come from Q charge times V. And so if you move this V over, then the charge necessary you'll be solving for the charge necessary. So if you divide this by the voltage, 12.0, then that will give you the amount of charge that needs to be moved. And if you do the math on that, you get 7.40 times 10 to the third, or 7,400 coulombs of charge that has to be moved. Part B states how many electrons per second flow if it takes 5 minutes to warm the formula. Well, you take the 7.40 times 10 to the third coulombs and you divide that by 1.60 times 10 to the minus 19 coulombs per electron. And then you multiply that by 1 over 300 seconds, which is 5 minutes. That gives you how many this is the total number of charges that are necessary. And then per second, if it's 5 minutes, it's 300 seconds. And so that's 1.54 times 10 to the 20 electrons per second. A battery-operated car utilizes a 12 volt system. Find the charge the batteries must be able to move in order to accelerate a 750 kilogram car from rest to 25 meters per second, then climb a 200 meter high hill, and then cause it to travel at a constant distance of 25 meters per second if it takes a force of 500 newtons to keep that going. And so this is basically 3 steps. You have to accelerate to 25 meters per second. And so that's 1/2 mv squared, kinetic energy, plus climb a 200 meter hill, so that's mgh, plus continue moving against a force of 500 newtons for a period at 25 meters per second. And so that's force times distance. And you use the 25 meters per second to figure out how far you go, if you go that for an hour. Okay? So let's fill in all these various parts. So you have 1/2 times 750 times 25 squared plus 750 times 9.8 times 200 plus 500 newtons times the distance. The distance, it was 25 meters per second, and you're going to go a total of 3,600 seconds. Okay, so you can put that in, 25 times 3,600 And so that gives you the total energy output that was done, and that is 4.67 times 10 to the 7th joules. So the total energy, or the total electrons that have to be moved, is QV again. And you know that you have a 12 volt battery, so you just take this result and divide it by 12, and it gives you 3.86 times 10 to the 6 coulombs of electrons that have to be moved, or coulombs of charge that have to be moved. Okie doke. Now we're moving on to a different section. And the next problem is problem number 19. Problem number 19 states, this is the section on electric potential in a uniform electric field. Membrane wall of a living cell is surprisingly large electric fields across them due to the separation of ions. What is the voltage across a 8 nanometer thick membrane if the electric field strength across it is 5.5 megavolts per meter? Big M stands for megavolts. And so 5.5 megavolts is 5.5 times 10 to the 6th volts per meter. And so that's the field. And the distance is 8 nanometers, which is 8 times 10 to the minus 9 meters. So the voltage across a distance, this is number 19 by the way, and that they use the symbol VAB from point A to point B, is equal to the electric field times the distance. So in this case, it's going to be 5.5 times 10 to the 6th times 8.00 times 10 to the minus 9. And that's going to be 4.4 times 10 to the minus 2, volts. 4.4 times 10 to the minus 2 volts. Number 22. A doubly charged ion is accelerated to an energy of 32.0 keV by the electric field between two parallel conducting plates separated by 2 centimeters. What is the electric field between these plates? All right, EV is not the same as V, just so you know, okay? So the electric field here is equal to 22.0 keV, which is equal to 22 times 2.2 times 10 to the 4th EV. And the distance we're looking at is 2 centimeters, or 0.02 times 10 to the minus 2 meters. So KEF is equal to Q times VAB, which is equal to Q. From up here, we know that VAB is ED, so we've got Q times E times D. So it's doubly charged. So if we solve this now, this whole thing for E, we end up with KEF, which is what this is, divided by QD. And so that's equal to 2.2 times 10 to the 4 EV. And to change that to joules, it's 1.60 times 10 to the minus 19 joules per EV. And so that's in the chapter, that conversion's in the chapter, and you divide that by 2 times 1.60 times 10 to the minus 19 times 0.02. And you get 8.00 times 10 to the 5 joules. Which makes sense if you take this and cancel this, and then you're dividing this number by 0.04. So that makes sense that you would get that. All right, number 26. A sphere has a surface uniformly charged with 1 coulomb. At what distance from its center is the potential 5 megavolts? What does your answer imply about the practical aspects of isolating such a large charge? So Q here is 1 coulomb, and V is equal to 5 megavolts, or 5 times 10 to the 6th volts. And so V is equal to KQ over R. So we're solving this for R now, so now that's going to equal KQ over V. And so this is 8.99 times 10 to the 9th times Q, which is 1 coulomb, divided by 5 times 10 to the 6th. And so the answer here is 1.80 times 10 to the 3rd meters, or 1.8 kilometers. And basically it tells you that because that's a huge distance, it's going to be practically impossible to isolate such a charge. Number 30. Number 30 states in a nuclear fission, a nucleus splits roughly in half. What is the potential 2 times 10 to the minus 14 meters from a fragment that has 46 protons in it? Okay, so you do this calculation the same way. V is equal to KQ over R. And so this is going to equal 8.99 times 10 to the 9th times Q. There are 46 protons, and each proton has a charge of 1.6 times 10 to the minus 19. And the distance is 2 times 10 to the minus 14. And so you end up with a voltage of 3.31 times 10 to the 6th. 3.31 times 10 to the 6th. The potential energy, the second half of this problem, says what is the potential energy in MeV of a similarly charged fragment at this distance? The potential energy, as we said before, is QV. So it's going to be 46 times 1.9 times 10 to the minus 19 times 3.31 times 10 to the 6th equals, well, also, got the conversion to MeV, equals 1 EV is 1.60 times 10 to the minus 19 joules. And so you end up with 1.53 times 10 to the 8th EV, that's what this conversion was. And then in MeV, that's going to be 153 MeV.